Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 5.2 on the characteristic equation. I'll teach you all about how to find the eigenvalues of a matrix, go over some properties of eigenvalues, and walk through lots of example problems. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. The eigenvalues of a matrix can be found from a polynomial called the characteristic polynomial of a matrix. The characteristic polynomial of a matrix is a polynomial that contains important information about a matrix, especially its eigenvalues. The characteristic polynomial is written as p of lambda, and it's equal to the determinant of a minus lambda times I. If A is an n by n matrix, the characteristic polynomial, p of lambda, can be written as a polynomial whose leading term is minus 1 to the n times lambda to the n. If A is a 2 by 2 matrix, the leading term of our polynomial is going to be lambda squared, and if A is a 3 by 3 matrix, the leading term of our characteristic polynomial is going to be minus lambda cubed. We can also write p of lambda in factored form, where lambda 1, lambda 2, all the way up through lambda n are the eigenvalues of matrix A. Let's now walk through two example problems where we'll find the characteristic polynomial of a 2 by 2 matrix and of a 3 by 3 matrix. Our characteristic polynomial p of lambda is equal to the determinant of a minus lambda I, and that's equal to 5 minus lambda. We're just subtracting lambda off the main diagonal entries. This determinant is going to be our main diagonal entries multiplied minus our off diagonal entries multiplied. If we multiply everything out, this gives us lambda squared minus 5 lambda plus lambda minus 5 plus 7. Combining like terms, we then get lambda squared minus 4 lambda plus 2. This is the characteristic polynomial of our matrix. When A is a 2 by 2 matrix, there's another formula that you can use to calculate the characteristic polynomial. I've written this formula up above in green, and it's just equal to lambda squared minus the trace of A times lambda plus the determinant of A. Notice that that formula only works for a 2 by 2 matrix. Let's now look at our second example. Our p of lambda is going to be the determinant of a minus lambda I, and that's equal to this determinant. The easiest way to evaluate this determinant is going to be using cofactor expansion across the first row because that row has the most zeros. This is going to be equal to 3 minus lambda times the matrix that remains after crossing out the row and column common to 3 minus lambda, and that's going to be 4 minus lambda times 2 minus lambda minus 0. Now we just have to multiply everything out. We have a 3 minus lambda, and on the inside, we're going to get a lambda squared minus 6 lambda plus 8. And then we just have to multiply every term. This gives us 3 lambda squared minus 18 lambda plus 24. And then we have a minus lambda cubed plus 6 lambda squared minus 8 lambda. When we combine like terms, writing them from the highest power to the lowest power, we get minus lambda cubed plus 9 lambda squared minus 26 lambda plus 24. This is our characteristic polynomial for our 3 by 3 matrix. Notice in our 2 by 2 matrix that our leading term was lambda squared, and in our 3 by 3 matrix, our leading term was minus lambda cubed. That's always going to happen. We're now going to use a characteristic polynomial to find the eigenvalues of a matrix. The eigenvalues of our matrix are the scalars lambda that are solutions to the characteristic equation defined as determinant a minus lambda I is equal to 0. The characteristic equation is just the characteristic polynomial set equal to 0. To find the eigenvalues of a matrix, we need to complete 2 steps. The first step is to calculate the determinant of a minus lambda I, and then the second step is to solve the characteristic equation determinant a minus lambda I is equal to 0. Let's now walk through 3 examples where we'll find the eigenvalues of a 2x2 matrix. In each example, we'll get different types of eigenvalues. Let's look at our first example. We'll begin by finding our characteristic polynomial determinant a minus lambda I. This is equal to the determinant 4 minus lambda, 2 minus 1, and 1 minus lambda. We multiply the main diagonal entries, and then we subtract off the off-diagonal entries. This gives us lambda squared minus 5 lambda plus 4 plus 2. So our characteristic polynomial is lambda squared minus 5 lambda plus 6. Our second step is that we take this answer and we set it equal to 0. We're going to have to factor this. We can factor this as lambda minus 2 and lambda minus 3. This gives us eigenvalues equal to 2 and 3. You can write it like that, or you can choose to write it as lambda is equal to 2, 3. This is an example where we have 2 distinct eigenvalues. Let's now look at our second example. We'll do the same thing as in example 1. We'll begin by calculating the determinant of a minus lambda I. You might want to stop the video and do this one on your own for some extra practice. We have 10 minus lambda, 4 minus 9, and minus 2 minus lambda. This is equal to 10 minus lambda times minus 2 minus lambda minus a negative 36. Multiplying everything out, we get a lambda squared plus 2 lambda minus 10 lambda minus 20 plus 36. Combining all the like terms, we get lambda squared minus 8 lambda plus 16. For our second step, we take our characteristic polynomial and we just set it equal to 0 and solve for lambda. Looking at this, we can see that we can factor this as lambda minus 4 times lambda minus 4, and that gives us lambda is equal to 4 and 4. You can also choose to write this as lambda is equal to 4, and then in parentheses, you just write multiplicity 2. That just means that there are 2 lambdas equal to 4. Let's now categorize this example. This is an example where we got 2 repeated eigenvalues. Hang with me. We have one more example to look at, and we're going to get eigenvalues that are different than we got for the first 2 examples. Our determinant of a minus lambda I is equal to 5 minus lambda minus 4, 3, and 4 minus lambda. Our determinant is then equal to 5 minus lambda times 4 minus lambda minus a negative 12. Multiplying everything out, we have a lambda squared minus 9 lambda plus 20 plus 12. This gives us lambda squared minus 9 lambda plus 32. In our second step, we're going to take what we just got, lambda squared minus 9 lambda plus 32, and we set it equal to 0. If you stare at this quadratic, you can soon see that there's no way that we can factor it without using the quadratic formula. Let me write down the quadratic formula in case you've forgotten it. If we have a lambda squared plus b lambda plus c is equal to 0, lambda is going to be minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. We'll now use this formula for the quadratic that we got, and we get our lambda is equal to negative b, so that's minus a negative 9, plus or minus the square root of our b squared, so that's minus 9 squared, minus 4 times 1 times 32. And we divide that all by 2 times 1. This gives us lambda is 9 plus or minus the square root of 81 minus 128, all divided by 2. Lambda then is equal to 9 plus or minus the square root of minus 47, all divided by 2. You might remember that the square root of negative 1 is equal to I. So that tells us that lambda is going to be 9 plus or minus I root 47, all divided by 2. In this example, we have no real eigenvalues. Let's now walk through an example where we'll find the eigenvalues of a 3 by 3 matrix. The first thing that we have to do is to calculate the determinant of A minus lambda I. We're going to subtract lambda off our main diagonal entries, so we get minus 1 minus lambda, 0, 1, minus 1, 3 minus lambda, 0, and then minus 1, 4, and minus 1 minus lambda. I'm going to choose to evaluate this determinant by doing a cofactor expansion across the first row. Our determinant is then minus 1 minus lambda times the determinant that's left when we cross out the row and column common to minus 1 minus lambda, and that's going to be 3 minus lambda times minus 1 minus lambda minus 0, and then we have 1 times the matrix that remains by crossing out the row and column common to 1, and that's minus 4 minus 3 minus lambda times minus 1. It's really important to not multiply everything out until you can see if you can factor out a term. So I'm just going to write our first expression as minus 1 minus lambda squared times 3 minus lambda. And then our last expression here is going to be minus 4 plus 3 minus lambda, and that's equal to minus 1 minus lambda. So let's add a minus 1 minus lambda. We can then see that we have a minus 1 minus lambda common to every term, and we can pull that out. And then what we have left is a minus 1 minus lambda times 3 minus lambda plus 1. Now we can go ahead and start multiplying things out. We have lambda squared plus lambda minus 3 lambda minus 3 plus 1. Combining like terms, we have lambda squared minus 2 lambda minus 2. Our second step is that we're going to take what we just got and we're going to set it equal to 0 and solve for lambda. This gives us minus 1 minus lambda is equal to 0, which gives us lambda is equal to minus 1. And then we have lambda squared minus 2 lambda minus 2 is equal to 0. Unfortunately, we can't factor this without using the quadratic formula, so let's go ahead and do that. We have lambda is equal to negative b, so that's minus a negative 2, plus or minus the square root of b squared minus 2 squared minus 4 times a, which is 1, times c, which is negative 2, all divided by 2 times 1. This means that lambda is going to be 2 plus or minus the square root of 4 plus 8, all divided by 2. This gives us 2 plus or minus root 12 divided by 2. Our 12 is equal to 4 times 3, so we can take out the square root of 4, which is 2. I'm going to come over to the left and write the answer. Lambda is equal to 2 plus or minus 2 root 3 all over 2 for a final answer of 1 plus or minus root 3. Our eigenvalues are then -1 and 1 plus or minus root 3. So for this problem, we ended up with 3 distinct eigenvalues. Now that we know all about how to find the eigenvalues of a matrix, let's learn a little bit about properties of eigenvalues. Our first property tells us that the eigenvalues of a to the k, where k is a positive integer, are the eigenvalues of a, each raised to the power k. I'll show you how to remember this. Let's start with the definition of an eigenvalue and an eigenvector. A times v is equal to lambda v. To see what the eigenvalue of a squared is, we're going to multiply both sides of this equation by a. On the left, we get a squared times v, and on the right, we can rearrange things and pull out the lambda and write it as lambda times a times v, and then substitute in that a times v is equal to lambda v, and that then gives us that a squared times v is equal to lambda squared times v. The eigenvalues of a squared are just then lambda squared. This gives us the formula that a to the k times v is equal to lambda to the k times v. This formula tells us that lambda to the k are the eigenvalues of a to the k. Let's walk through an example and see how this works in practice. We're asked to find the eigenvalues of matrix A cubed. All we have to do is find the eigenvalues of A, and then we'll know that the eigenvalues of A cubed are just lambda cubed. To find the eigenvalues of A, we're going to do 2 minus lambda, 2, 3, 1 minus lambda, just subtracting lambda off the main diagonal. This gives us the main diagonal entries multiplied minus the off-diagonal entries multiplied. If we multiply everything out, we have a lambda squared minus lambda minus 2 lambda plus 2 minus 6. This gives us lambda squared minus 3 lambda minus 4. We'll now set this equation equal to 0 and go ahead and factor it and find lambda. We can factor this equation as lambda plus 1, lambda minus 4, and that's equal to 0. So this tells us that lambda is equal to -1 and lambda is equal to 4. We can now find the eigenvalues of A cubed, and they're going to be our lambdas cubed. So we get a value of -1 and then 4 cubed, which is 64. Our eigenvalues of A cubed are then -1 and 64. Our second property tells us that A and A transpose have the same eigenvalues, but usually not the same eigenvectors. Let's see how to remember this. If A and A transpose have the same eigenvalues, then the determinant of A minus lambda I has to equal the determinant of A transpose minus lambda I. I'm going to now show you how these two are equal. We'll start with the determinant of A transpose minus lambda I, and we'll write it as the determinant of A transpose minus lambda times I transpose. This is just like multiplying by I because I is equal to I transpose. We'll then do some rearranging and take the transpose to the outside and write it as determinant of A minus lambda I quantity transposed. We'll then use the fact that the determinant of a matrix transposed is the same as the determinant of the matrix, and that tells us that the determinant of A minus lambda I transposed is just the determinant of A minus lambda I. Because these two quantities are equal, A and A transpose have the same eigenvalues. I want to make a note that transposition, in other words, taking the transpose of a matrix, changes the direction of a linear transformation, and hence, usually, its eigenvectors. So A and A transpose don't usually have the same eigenvectors. Our third property tells us that the eigenvalues of A inverse, where A is assumed to be an invertible matrix, are the reciprocals of the eigenvalues of A. Let's start with our definition A times V is equal to lambda V, and I'll show you why this is true. To find the eigenvalues of A inverse, we'll multiply both sides of this equation by A inverse. This gives us V on the left, and then on the right, we'll do some rearranging and pull out the eigenvalue and write it as lambda times A inverse times V. We'll then divide each side of the equation by lambda, and on the left, we'll have 1 over lambda V, and on the right, we'll have A inverse times V. If we compare these two equations, you can see that 1 over lambda is an eigenvalue of A inverse. I've written down this formula in green so that you can remember it. Let's now do an example. We're going to find the eigenvalues of A inverse, and we're given matrix A. There are two steps that we're going to have to follow. We first have to find the eigenvalues of A, and then the eigenvalues of A inverse are just going to be the reciprocal of the eigenvalues of A. To find the eigenvalues, we take the determinant and subtract lambda off the main diagonal. This one's going to be a little bit easier because we have a 0 in the upper right-hand corner, so we just get 3 minus lambda times minus 1 minus lambda. We then set that equal to 0 and solve for lambda, so we get lambda is equal to 3, and lambda is equal to minus 1. Now let's find the eigenvalues of A inverse. The eigenvalues of A inverse are just the reciprocal, so our eigenvalues are going to be 1 over 3 and 1 over negative 1, which is just negative 1. Hang with me, we have 2 more properties to go. Our next property tells us that the determinant of a matrix is just the product of its eigenvalues. We saw at the beginning of this video that the characteristic polynomial of a matrix is P of lambda, and it's equal to the determinant of A minus lambda I, and can be written in factored form where lambda 1, lambda 2, all the way up through lambda n are the eigenvalues of matrix A. To find the determinant of A, we're going to go back to this equation, and we're going to let lambda equal 0. This gives us P of 0 is determinant of A, and we get this expression. The negatives cancel out, and then we have the formula that the determinant of A is the product of its eigenvalues. That's a really great formula because as soon as you know the eigenvalues of a matrix, you can find the determinant. Let's now look at our last property. Our last property tells us that if 0 is an eigenvalue of A, then A is not invertible. This relates back to our invertible matrix theorem that we looked at in section 2.3. We'll use the formula that we just found to see why this is true. The determinant of A is going to be equal to 0 if any lambda is equal to 0, or any eigenvalue is equal to 0. We know from the invertible matrix theorem that A inverse does not exist when determinant A is equal to 0. So that tells us if 0 is an eigenvalue of A, then matrix A is not invertible. Let's now walk through an example that utilizes some of the properties that we just learned. We're going to suppose that the characteristic polynomial of a matrix is given by P of lambda is equal to lambda squared times lambda minus 2 times lambda minus 4. The first question that we're going to answer is what is the size of A? We're first going to find the eigenvalues of our matrix. We can find the eigenvalues by setting P of lambda equal to 0. So we have lambda squared times lambda minus 2 times lambda minus 4 is equal to 0. And that tells us that lambda is equal to 0, 0, 2, and 4. We have 4 eigenvalues. Because we have 4 eigenvalues, we can say that our matrix A is a 4 by 4 matrix. Let's now look at our second question. We're asked if A is invertible. Notice from part 1 that 0 is an eigenvalue. Because of this, we can conclude that A is not invertible. Our last question asks us, how many eigenspaces does A have? To answer this question, we're going to have to go back up and look at the eigenvalues of matrix A. Notice that we have 3 distinct eigenvalues. We're going to have an eigenspace for every distinct eigenvalue. So that means that our matrix A has 3 eigenspaces. The last topic that we'll look at is how performing row reduction on a matrix may change its eigenvalues. Row reduction, meaning just applying elementary row operations to a matrix, generally changes the eigenvalues of a matrix. If we have a 2x2 matrix A, we put it in reduced echelon form, our reduced echelon form is going to be our identity matrix. The eigenvalues of our identity matrix are going to come from the equation 1 minus lambda squared is equal to 0, and is going to give us eigenvalues lambda is equal to 1 and 1. We've done lots of examples of eigenvalues of 2x2 matrices in this lesson, and we never got eigenvalues equal to just 1 and 1. Row reduction usually changes the eigenvalues. Let's look at an example so you can see exactly how this works. I'm first going to find the eigenvalues of this matrix. We have determinant A minus lambda I, and it's equal to 4 minus lambda, 2 minus 1, and 1 minus lambda. I always think it helps to do an example so you can see how row reduction usually changes the eigenvalues. Our determinant is equal to 4 minus lambda times 1 minus lambda minus 1 times 2. This is equal to lambda squared minus lambda minus 4 lambda plus 4 plus 2, which gives us lambda squared minus 5 lambda plus 6. We're now going to set this equal to 0, and we'll factor it as lambda minus 2, lambda minus 3, and we get our eigenvalues 2 and 3. Let's hold on to those for a minute. And now what we're going to do is we're going to take A and we're going to put it in echelon form. To put it in echelon form, I'm going to take row 2 and replace it with row 2 minus 1/2 row 1. This then gives us the echelon matrix 4 minus 1, 0, 3/2. Notice that this matrix is a triangular matrix, so the eigenvalues are just going to be the entries along the main diagonal. The eigenvalues are 4 and 3/2. The eigenvalues of matrix A were 2 and 3, and the eigenvalues of an echelon form of matrix A were 4 and 3/2. These eigenvalues are not the same, and that's because row reduction generally changes the eigenvalues of a matrix. Be sure to check out the next video in this series, where I'll teach you all about how to diagonalize a matrix and raise a matrix to a power.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.